welcome Monika Aidelsburger. So Monika is an eminent young researcher from Ludwig Maximilian University of Munich, and I'm very excited to hear her talk about quantum simulation again. And this time we'll be talking about engineering and understanding quantum systems atom by atom. So fascinating quantum optics world, fascinating quantum world engineers. So Monika, thanks for being here. Thanks for accepting the invitation. And the floor is yours.
Okay, thank you very much for this kind introduction. Yeah, I'm very happy to be here and share some of our work. Mostly, I would like to introduce our experimental platform and give you, explain to you a few pictures behind the scenes maybe, and then at the end of the talk to give you a little bit of an outlook where the field is going, or where I think new developments may arise. Okay, so let me start by first giving a very brief motivation about why we are interested in quantum simulation in the first place. And you heard, of course, many talks about these topics. So there are a lot of exciting developments, and we hope that we can actually use quantum systems in order to develop new applications, for instance, for quantum computers, metrology, sensing, communication, and many, many other examples. Now, in order to be able to do that, what we actually need to do is engineer quantum systems where we can controllably turn off or on and off or modify the interactions between particles in order to engineer entangled states, for instance. And this is a very challenging task from an engineering point of view, but also from a theoretical perspective. And the reason is that the computational complexity grows exponentially. So if you want to understand a quantum system that consists of many constituents, it becomes extremely challenging to compute exactly what the properties are. But this is something that we need to know if we actually want to harness the properties of quantum many-body systems. So one solution was proposed by others also, but the most famous one being Richard Feynman, is the idea of building a quantum simulator. The idea is really that we build a system in the lab where we control each individual quantum particle, and we put a large many-body system together, atom by atom in our case. And then the idea is to actually perform experiments in a controlled way in order to learn more about the properties of these systems, which then allows us to refine maybe theoretical tools, numerical tools, and then apply them to more general quantum many-body systems, and then eventually use our knowledge in order to design new applications and actually make quantum many-body systems useful for applications. Now, this is a very intriguing idea, and it turns out that there are many different ways you can tackle this problem. So you could build quantum many-body systems based on many different types of constituents. So there are many different examples, for instance, superconducting qubits, trapped ions, Rydberg atom arrays, and in our case, neutral atoms that are trapped in optical lattices. There are actually more examples, so that's just a small selection. And you will realize that these systems, they are also very prominent when it comes to the development of quantum computing platforms. So everybody has heard about the Google chips and the superconducting qubits, but similarly, also trapped ions, Rydberg atom arrays, and also atoms and lattices are pursued as potential platforms for quantum computing. Okay, so how does that work? So let me explain you a little bit how these images of neutral atoms and optical lattices are produced. So what you actually see here is a collection of particles, and each one of these spots or bright spots corresponds to one single atom that emits a few thousand photons, which we then collect with a high-resolution imaging system on a camera chip. Okay, so how do we get there? And this is a picture that we've taken in our cesium lab a couple of years ago during the building up of the experiment. And I'd like to use that one in order to walk you through the different stages. Okay, so what do you need? The first thing you need is actually a vacuum system, because in the end, we have a cold cloud of atoms that we trap in laser beams. Okay, so what you see here on the very right, that is wrapped in aluminum foil, is an oven. And what we do is we put in 5 to 10 grams of material, in this case cesium, and then in order to make them diffuse into the vacuum system, we heat it up. And in this case, this would be about 80 to 90 degrees Celsius. For ytterbium atoms, for instance, it would be around 402 degrees Celsius. So the atom diffuses into this vacuum system. but they are extremely hot. So we somehow need to find ways to slow them down or cool them. And what you see here, I hope you can see actually my mouse, is a steel tube where there are coils wrapped around. And this is the so-called Siemens law, where we first slow down the atoms by shining in a counterpropagating laser beam. This laser beam is near resonant to an internal transition. So the atoms absorb many photons, they scatter many photons from this counterpropagating laser beam and experience a pushback due to the recoil kick introduced by the photons. And if you have many scattering processes, this can gradually slow down the atoms such that you can capture them in a magneto-optical trap. And in order to cool the atoms in a magneto-optical trap, we shine in additional laser beams from all three directions in space. And again, we choose them to be near resonant, such that we can cool them down by compensating the Doppler shift. So the idea of laser cooling really is that atoms only can absorb photons if they counterpropagate with the laser beam. And then whenever they absorb a photon, they get a pushback. And by that, you can basically slow down the atoms or cool them from all three directions, because whenever they want to move along a certain direction, they get a photon recoil kick from that beam. So this allows us to cool the atoms to very low temperatures on the order of microkelvin. Now, in this chamber, this is actually fully made of steel. It is hard to get very close to the atoms with our imaging system. So in order to be able to do that, we actually move the atoms from this section to a different section in the vacuum system. So in the end, our vacuum chamber is actually of an L-type configuration. So we move them to a new chamber, and this chamber is made full of glass. Now, how do we move the atoms? This is actually done by generating optical potentials. So let me give you the simplest example. You can take two counterpropagating laser beams, as shown here in red with these red arrows. Now, if they have the same frequency and the same polarization, they will produce a standing wave. And now, as opposed to the laser cooling beams, those are very far off resonant from any internal transition. So there's basically no scattering of photons. However, due to the presence of this intensity, the atoms experience an AC Stark shift or so-called light shift. So proportional to the intensity of the pattern, there's a potential that develops, and the atoms see this as valleys and mountains. So the atoms actually preferentially sit in the minima of this potential. And if you actually go ahead and plug in numbers for suitable laser wavelengths, but also for available laser powers, you find that this effect, that the atoms actually see a potential energy landscape induced by light, is extremely small. If I assign a temperature scale to this, it will be on the order of a millikelvin. So typically, if you were to do that with a hot gas of atoms, nothing happens. The atoms wouldn't be trapped in such a potential energy landscape. However, because we pre-cooled them, we had this laser cooling step before where we go to microkelvin temperatures, they can actually be trapped in this potential. So now, because it's a 1D interfering lattice, you have atoms that accumulate in the standing wave, and they actually form type of pancakes. So they are trapped in space. But now, because you actually control the potential, you can also manipulate it. So what happens is, if we detune one of these two frequencies of these two interfering laser beams, this standing wave starts to move. And it actually drags the atoms along with it in a conveyor-like belt configuration. Okay, so we trap the atoms in this pancake-like configuration, and then we suddenly shift it in 30 milliseconds, about 43 centimeters, into the final science chamber. And the final science chamber then has very good ultra-high vacuum conditions, 10 to the minus 11 millibar, the low 10 to the minus millibar regime. And this is important in order to have a long lifetime of our atoms. So you should really think about it as a cloud of atoms as being held by the laser beams in vacuum. The atoms are extremely cold. We go down to the nanokelvin temperature scale, but everything else is actually at room temperature. So what isolates the atoms from the environment is really the vacuum conditions. Now, this is a picture or a zoom in of the science cell. You see that it's fully made of glass, and it provides very good optical access from the top and bottom window, but also it has 11 side ports, which we can use in order to shine in additional laser beams in order to generate different types of potential energy landscapes for our atoms. And the state of the atoms of this many-body system after the last cooling step which in our case is evaporative cooling, for bosonic atoms would be a Bose-Einstein condensate. Depending on the atomic species and the isotope, we can actually also work with fermions. And if we cool them down to low enough temperatures, we would form degenerate Fermi gases. Now, the difference between the two is that, in a nutshell, what you should think of a Bose-Einstein condensate is that even if you have millions of atoms, they all accumulate in the lowest energy eigenstate of your system, which in the schematic drawing would be the ground state of an harmonic oscillator. For fermions, instead, due to the Pauli exclusion principle, they would fill up all the available energy levels up to the Fermi energy. And in the schematic drawing that I show here, we have two different internal states of the fermions, and therefore each energy level is occupied by two fermions. Now, if you actually put all of this together in the end, and you implement all the evaporative cooling laser beams and lattice lasers in the end for experiments, the setup looks, like this. And this is exactly the same table that I showed on the previous picture, but now adding all the other optics, so you can actually not see the final science cell anymore, or the final glass cell. It's hidden behind one of these yellow pillars. And in the lower left, you see the picture that I've shown on the previous slide, which actually shows cold cesium atoms trapped in a square optical lattice. Okay, so similar to the transport lattice, we can now generate potential energy landscape by interfering different types of laser beams. And because our initial configuration is a BEC or a Fermi gas, if we want to study the ground state properties of a certain model Hamiltonian, we now adiabatically transform the atoms that are cold in a harmonic trap adiabatically into a periodic potential that is generated by this interference. So again, here, this is a 1D configuration. And the distance between neighboring sites is lambda half, where lambda is the wavelength of the laser beam. So typically, this is on the order of half a micron. Okay, so what can we do with it? We can prepare, for instance, a square type optical lattices. We can generate graphene type optical lattices. And what is shown in the upper right corner, that's an example from Cambridge, from Uli Schneider's group, where he overlapped 4 standing waves in order to generate a quasi-crystal. If we load atoms slowly enough at low temperatures in such a periodic energy landscape, then the dynamics is actually described by Hubbard models. And Hubbard models are characterized by 2 main quantities: the tunnel coupling J between neighboring sites and the Hubbard interaction energy U if more than one atom is located on one site. And this has been extremely successful in order to perform quantum simulation experiments of condensed matter model Hamiltonians. This model, which has this kinetic energy term, the hopping term, and the interaction, is actually the simplest one that allows you to describe strongly correlated phases of matter, that is, electrons in an ion crystal. So for instance, there's a transition from a metallic state or a superfluid to an insulating state, which is driven just by turning on the interactions. And this can actually be done in our quantum simulation experiments. We can control the interaction energy strength with so-called Feshbach resonances. So practically what we do, we change an external magnetic field, which then allows us to control the interactions. So this has been an extremely important model system. And now there are 2 types of questions that I would like to address in a little bit more detail. The first one is, how do we actually observe and control the atoms in this lattice? And the second one, what type of model Hamiltonians can we simulate despite the simple Hubbard model that I put here on the slide? And I give a selection, or one main example. Of course, there are many different ways in order to make these Hamiltonians more complicated. Maybe on a side note, what you see here is an introduction to analog quantum simulations. What we aim at doing is implementing certain model Hamiltonians H and then studying its properties directly. This is in contrast to universal quantum computing, where you would try to develop a quantum computing platform with single and 2 qubit gates, where you can then implement any type of quantum computing algorithm or simulate Hamiltonian dynamics by trotterizing the Hamiltonian into different steps. Okay, so now let me give the 2 main examples of the types of experiments that we can do. The first one I basically already mentioned is to study ground state physics. Here, the idea is to really start with a cold cloud of atoms and then be as gentle and adiabatic as possible in order to manipulate the system. So we slowly load the atoms into the lattice, and then we can also adiabatically change the parameters of this model. So here, that's an example that I've taken from Markus Greiner's lab in Harvard, where you see the example of a Fermi-Hubbard model at half filling. So the blue and red balls indicate two different spin components, and they can be investigated under a microscope. So I'll say a little bit more about this later. The idea is that with this microscope, you can really see each individual atom in the trap and even in a spin-resolved way. And the Fermi-Hubbard model at half filling has antiferromagnetic correlations, which can be revealed by the quantum gas microscope. So this is the first type of application, looking at ground state physics and studying the phase diagram of a certain model. The second type is a little bit different. Here, the idea is that we prepare well-defined initial states, but they don't have to be necessarily the ground state. This could be a certain configuration of atoms in the trap, which we can realize by just placing the atoms at different locations. And then we turn on the Hamiltonian and look at time evolution. And this is a very hard problem, which numerically is very, very challenging to simulate. What can we study with that? So first of all, it's quench dynamics, it's relaxation of quantum many-body systems. But if you think about it, it really allows you to address fundamental questions regarding thermalization. So now the system that you are having is actually a quantum many-body system that is prepared in your vacuum chamber. It's in a pure initial quantum state. It's well isolated, so there's no connection to any thermal bath whatsoever. And then you ask, if you let time evolve, what happens? So the naive answer would be, well, not much. So you have unitary time evolution. The system will remain in a pure state, and it will just evolve as a function of time. The interesting fact, however, is that if you look at the subsection of this as a small part of your two-dimensional system or one-dimensional chain, you will find that locally, the state will look thermal. So even if there's unitary time evolution in your system, the quantum many-body state appears to be thermal if you look at a local observable. And there are very interesting phenomena that happen. For instance, in the presence of disorder, you find that there are many-body localized phases, and there are many open questions, for instance, regarding two dimensions, where it's still highly debated if such a phase can occur. And the example that I show here on the slide is from Emanuel Bloch's group, where they have looked or explored localization in the presence of disorder for a 2D system. So initially you see only half of the harmonic trap is occupied with atoms. And then you ask what happens if you let it evolve into the second half of the system. And indeed you find if there's disorder present, the system will not completely thermalize, at least on the timescales that are shown here. There will be a memory of the initial state, meaning that if you look at 187 tunneling times, you still see a bias towards the left half of the system where initially you have put your atoms. All right, so now back to the question, what type of Hamiltonians we can actually simulate. And I already mentioned that Hubbard models is something that we can naturally access in our systems. And this connects us to model Hamiltonians that are used in order to study strongly correlated states for electrons in materials. Now, if you think about these electronic systems, there are a lot of interesting phases of matter that would be nice to study in a quantum simulation environment. And the example that I've picked are topological phases of matter. And specifically, our experiments have been developed in order to study integer and fractional quantum Hall insulators, where there are many open questions, in particular for the fractional quantum Hall insulators, which emerge which arise in the presence of interaction. So those are true many-body topological phases, which would be very interesting to access in quantum simulation experiments in a controlled way. Now, integer quantum Hall systems arise in the presence of an external magnetic field. So this is shown here as a schematic in the upper left corner. This shows a Hall bar geometry where you can measure the transverse Hall voltage and the longitudinal voltage. And if you send a current through the sample in the presence of an external perpendicular magnetic field, there are plateaus that appear in the transverse Hall resistance. Now, in the presence of interactions, there are many plateaus. Let me remind you about the simple integer quantum Hall effect. Same schematic, you send a current through your Hall bar geometry and you measure the transverse Hall resistance. Now, in the classical limit, there's actually a linear relation between the applied magnetic field and the transverse Hall resistance. This is used in order to calibrate the charge carrier density. So that's this linear slope down here. However, if you have a two-dimensional electron gas and large enough external magnetic fields, there's a deviation from this linear behavior, and you see these plateaus arise. And the value of these plateaus can be determined with extreme precision. And this is the essence of the integer quantum Hall effect. Now, because the precision is so high, it's immediately useful for applications. And it plays a role now also in the redefinition of the SI units, which has been done in 2019. So the value of these plateaus is actually independent of the microscopic details of the sample. And it's only given by natural constants, the Planck's constant and the charge of an electron, and integer quantities. And these integer quantities, they are given by the topological properties of the energy bands that are occupied with electrons. So that's an extremely interesting situation, which becomes even richer if you now add interactions. Okay, we would like to study such a system in cold atom experiments. Our atoms, however, are charge neutral, so it's very challenging to access any of these physics, because if we apply a magnetic field to our system, the only thing that happens is that the energy levels change according to the Zeeman effect, but we don't have any Lorentz force or anything that would give rise to a Hall effect. Now, the way we actually simulate such systems in the lab is by periodic driving. And I give you a very simple example, not a very simple example, just a brief intro in how that works without going too much into the details. The idea is that you now have your controllable model Hamiltonian in the lab, so you can actually periodically change the parameters as a function of time in order to make your system time dependent. And if you do that at a very fast driving frequency, the atoms will see an effective Hamiltonian, which is essentially a time average over this fast driven dynamics. And formally, this means that you can describe the system stroboscopically according to a new Hamiltonian HF, which is this time averaged one. So adding periodic driving to your system allows you to engineer new Hamiltonians that otherwise you would not be able to naturally access in your system. Now, this is a detail for now, but it also means that actually, because you have this driven system, energy is not confined. The atoms can absorb quanta from the drive and emit into the drive. So we have a quasi-energy spectrum. So if you look at the two-band model, there would be infinite repetitions of those. But in essence, what I want to give you as a takeaway message is that you can add periodic driving to your system in order to engineer new Hamiltonians. Now, let me give you one example to convince you that it actually works. So you may ask, okay, if you now are able to use periodic driving to engineer Lorentz force type dynamics or magnetic fields, how would that look like for your charge neutral atoms? Okay, so let's take the simplest example. I would like to have a situation where I have a particle, like an electron, and I apply an external magnetic field. So we know the electron would actually move on cyclotron orbits. Now, let's see if we can do something similar with charge neutral atoms. Now, what we do is we actually place a single atom into a very tiny lattice that consists of only 4 sites, and we look at its dynamics. So this data point here shows the initial location of the atom, and then we track it as a function of time. Now, what you find is that indeed the particle starts to move along a certain direction, here towards the right, but then it does get deflected and performs some type of chiral motion. And this actually resembles the cyclotron orbits that you would expect from electrons moving in an external magnetic field. Now, this is not a nice circular orbit, but the reason for that is that we have a highly discretized lattice that consists of only 4 sites. If you actually add more sites to your system, you can reproduce this very nice circular orbits. This is an example that I've taken from Sylvana Saben's group in Paris, where they have implemented this with dysprosium atoms. So the original experiment is from 2011, it's already very old, and these nice circular orbits, they are from 2020. All right, so this allows us now to generate artificial magnetic fields. But actually we want to do more, right? We want to recreate something that reminds us of the integer quantum Hall effect. So maybe we should think about how to do transport experiments. How do we actually recreate something that we know from solid state, where we can measure transverse Hall voltage? does that actually work? What does it mean? This is a very different situation. Here we send a current through the sample and we measure the transverse Hall voltage. And it turns out that despite our system being very different, you can generate a very similar situation. So now imagine you have a cold cloud of atoms sitting in your lattice potential in your harmonic trap. And now you apply a force to your system. So the force is actually something like a potential energy difference between the two ends of your system. What actually happens is that the system undergoes Bloch oscillations, but then on top of that, there's a Hall velocity that develops transverse to the force that we apply. And this transverse velocity is very similar to a Hall deflection of electrons in the presence of a magnetic field. So we expect that the atoms, if we apply a force in one direction, move sideways. And indeed, if we now completely fill one band, as in the electronic version of the integer quantum Hall effect, we would expect that the center of mass motion of this is proportional to this quantity that I briefly shown on the previous slide for the integer quantum Hall effect, the Chern number, the topological invariant characterizing the band. So just from analyzing the transverse motion and the slope, we can extract the Chern number, the topology of the band, which is exactly analogous to the integer quantum Hall effect. And this is what you see here. So that's the linear deflection of the cloud as a function of time. And from the slope, we can simply evaluate the Chern number or the topological invariant of the band. And this is actually remarkable. So let me just summarize that in a second. So this is a Hall deflection experiment. Now, not only do we have charge neutral atoms where we engineered an artificial magnetic field, this Hall effect was actually also measured with bosonic atoms, and electrons are fermions. So this system is actually completely different from the original one that we wanted to study. And this really highlights the idea of quantum simulation. What we want to do is actually study the properties of a model Hamiltonian. We develop techniques in the lab that allow us to study its properties, but those can be completely decoupled from the original system that we were interested in. The main goal is really to recreate the Hamiltonian itself. Okay, so let me show you one other fun experiment that we did more recently. You know that in quantum Hall systems, what is interesting is what happens at the edge. So you have an insulating bulk and topological edge modes at the boundary of the system. So if you have an interface between your quantum Hall material and vacuum, there are topologically protected chiral edge modes that transport the current along the edges of the system. So this is a defining feature of topological systems. And this is something that we wanted to study in our cold atom quantum simulator. Now, if you now go back to the system that I showed you in the previous slides, we have a cold cloud of atoms that is trapped in an optical potential, and then there's a harmonic confinement introduced by the laser beams. So the question is, where's an edge? So how do we generate a topological interface? Because there's a smooth variation from the center of the trap to the edges. And we came up with two techniques that allow us to actually see the edge modes directly with cold atoms. Now, the first thing that we did was to implement a very tightly focused laser beam. So this is illustrated over here. So we have a high NA objective. We have a laser beam at 1064 nanometers that we focus to a small spot, and we generate a BEC in the small spot. So this generates a localized wave packet in real space. And the idea behind that is that we want to generate a cold sample of atoms that we can directly use to populate the edge of the system. So we move our atoms to the edge and then hope that most of them end up in this chiral edge mode. Now, the second ingredient that we need is a topological edge. And the idea is to actually engineer a potential energy step that blocks half of our lattice. So we want that the atom can move in some region of space, but then that there's a sharp wall that prevents the atoms from exploring the rest of the lattice. So in order to do that, we actually need a way to shape the intensity profile of our laser beams such that we can engineer such a potential step. And what you see here in this picture is a digital micromirror array. So in the center of this image, there are 1000 times 1000 little tiny mirrors that you can switch on and off. And if you send a Gaussian laser beam onto this array, you can actually turn the intensity of the laser beam off in 1/2 of the system. So you can generate a dark region and a bright region, and then project this into the plane of the atoms. So if you look at the 2D plane, it looks basically like this. We have, in this case, actually a hexagonal optical lattice, not a square lattice. we have a localized wave packet in real space, a BEC, that we move close to the edge of the system. And this red region here would be this repulsive wall where we block the atoms from actually going there. Now, in our case, this wall has a steepness or stiffness of about 2 to 3 lattice constants. And you see that this is actually a very small length scale. So the lattice constant in our case is 287 nanometers. Okay, so let's see what happens. Again, we actually track the motion of our atoms in real space. This is the initial wave packet. So the blue region is a few hundred atoms that are trapped in this dimple trap, so in this tightly focused beam. And then we release it into the hexagonal optical lattice. And the background just means there are no atoms. The dashed line indicates where we block the atoms from going there. So it's actually the center of this disk is completely blocked. Now, as we let the atoms evolve as a function of time, you would expect that the wave packet simply expands. Okay, if there's no topology, the atoms will just explore the rest of the lattice. There's nothing that prevents them from going there. However, now we have this disk-shaped region that is blocked, so it's like a bucket. And we have the topology, so we have non-trivial topological properties in terms of Chern numbers. And what you see if you let the wave packet evolve is that it actually starts to wrap around the outside of this disk region that we blocked in space. And this really directly reveals the chiral nature of the topological edge mode in our system. Now we can also control the chirality of this edge mode, so we can make the atoms move in the opposite direction and take the difference images, and this is what you see here. So we have one edge mode that wraps around clockwise, one edge mode that wraps around anti-clockwise, and the difference image nicely highlights that the atoms really explore the outside of the disk. And now we actually have full control over the properties of the edge. We can make it be a straight line, we can play with the sharpness of the edge, we can play with the height of the potential step in order to study what is needed in order to have topological edge modes emerge in our system. All right, so now let me talk a little bit more about how we produce these images where you saw individual atoms trapped in the lattice. So this goes back to the cesium images that I showed in the beginning. And here for quantum gas microscopy, the idea really is that we want to take images of isolated atoms that are trapped in the lattice. And the way this works is that we ramp up the lattice to be very, very deep. And very deep means on the order of a few hundred microkelvins in temperature. And now in order to make the atoms bright on the camera, we shine in near resonant laser beams that scatter many photons, which would heat the atoms, but we choose the properties of these photons such that we cool at the same time. So we apply heating and cooling, if you wish, which allows us to scatter a few thousand photons and then take images like this. And this is done using this high NA objective. In this case, it's a numerical aperture of 0.8. And this large angle collects the photons and directs them towards our CCD or CMOS camera. So here you see a collection of dilute atoms where you clearly identify individual atoms. Now this allows us to evaluate local observables. So for instance, we can now go ahead and measure the mean density on a certain site in the lattice, but we can also measure more complicated observables such as correlation functions. So we can ask questions, if you find an atom on a certain site, how likely is it that there's also an atom on the neighboring site? But at the same time, you can also use this objective in reverse, which is something that I showed with the DMD to generate the potential edge. You can use these objectives to locally manipulate the atoms in the lattice as well. And then you can actually evaluate the performance of your imaging system. If you look at each one of these little bright spots, this actually directly gives you the point spread function of your imaging system. And you can also evaluate the signal to noise, like how many photons or how much signal do you collect from one atom as opposed to the background peak, which is shown here in this dark color. Now, there are many different types of quantum gas microscopes out there by now, both for bosonic atoms and fermionic atoms. And what is now the next step in the development of these quantum gas microscopes is really to make large and homogeneous system sizes. And this is something that I want to briefly show you, which is something that we have worked on in our cesium experiment. So let me just emphasize this a little bit. Previously, I told you that because we trap the atoms in space using Gaussian laser beams, there's an additional harmonic confinement. And as you actually see, for instance, in this image of potassium atoms from the Zwirlein group, which is shown here in orange, where you see a density profile that has more atoms in the center, and then it weakly decays towards the edges of the system. And because of this additional harmonic confinement, it actually also means that if you have a quantum simulation experiment, not each one of the lattice sites is at the same potential energy. There's this additional curvature, but if you want to have reliable simulation experiments, you actually want to get rid of that. So you need to flatten your trap. And the second comment I wanted to make is that, of course, we are also developing new techniques in order to engineer different model Hamiltonians to perform more complicated quantum simulation experiments. So let me show you the newest results, or some of the newest results from our cesium experiment, where we have worked on generating these large homogeneous system sizes. So here you see mod insulating state, or an array of atoms where each site is occupied with a filling or probability of 98%. And the system size is 50 by 50. So these are about 2,500 atoms, a bit more than that, in fact. And the bottom of the system is completely flat. The bottom of the trap is completely flat. And we do that, again, by using these digital micromirror devices, which we can use to shape the intensity of our laser beam. So we actually apply a repulsive box, a repulsive wall, similar to the edge state project. And because there may be a residual curvature at the bottom of the trap, we also flatten it. So we shape the intensity in order to compensate for this curvature. Now, let me add one slight comment. So if you look at these images, you may say, well, okay, so these are 2,500 atoms, but you can actually not resolve them, right? You told us you can build quantum gas microscopes to resolve individual atoms in the trap, but that's actually not really the case on these images. And this is true. However, there are two things. So first of all, the distance between neighboring sites is extremely small. So it's 380 nanometer only. We do that in order to have a large coherent tunnel coupling between neighboring sites. But we can actually reconstruct these images because there's a lot of information that we have about the system. So what is that? So first of all, we know that it's a lattice grid. So we know it's a square optical lattice. And we can actually reconstruct the lattice constant and the absolute position of the grid. And we do have the signal from each individual atom, which I've shown you on this slide. So from each isolated atom, we know exactly the response function, which is the point spread function. So if you have a 2D grid, like the one shown here with the white dots, the density distribution that you measure is actually the convolution of the location of the atoms with the point spread function. So in the end, looking at this and reconstructing the occupation just means you have to solve this deconvolution task in order to get the density back. Now, this turns out to be still an extremely challenging problem. And in order to solve it, we actually have developed an unsupervised machine learning approach. This is summarized in a paper that I show on the next slide. Let me just give you the brief idea. So the idea is that you take experimental snapshots. These white dots show the locations of the lattice positions. This is the image that you would get out of the experiment. And then the autoencoder architecture makes a kind of dimensional reduction. It learns where the atoms sit. So it gives you an occupation matrix of zeros and ones. And then it minimizes the difference between the convolved image and the original one that you put in. And with this, we get actually a very good reconstruction fidelity of more than 98%. So let me just show you this example. That's the square shape sample that I showed you in the beginning. And on the right, you see the reconstructed density, which we can do for half filling of more than 96% in fidelity. And this is summarized in the paper down here. And yeah, so with this, I can stop, I think. So yeah, no, with this I can stop. I think there's just one comment maybe that I want to make. We are developing techniques in order to not only simulate artificial magnetic fields, but just to mention what we actually want to do is study lattice gauge theories, which are a bit more complicated than Hubbard models. They're more challenging to simulate, but they would open the door to other areas of physics that would allow us to study also high energy physics problems, or maybe go towards topological quantum computation. And what is needed for that, in our opinion, or that's the platform that we are developing, is additional local control. So we want to combine our optical lattices with a tweezer array that allows us to locally manipulate the atoms in the lattice combine all of that, and then this would give us a platform to study lattice gauge theories and widen the range or the application of our quantum simulation experiments significantly beyond applications in condensed matter and Hubbard model type simulations. And yeah, so this is a very exciting direction. Many people are working on this, combining optical lattices with tweezers, also to speed up our experimental cycle times. And there are a lot of great people in my team working on this. And in case you got interested, we are always looking for motivated people to join us. So yeah, thank you very much.
Thank you very much, Monika. Wonderful talk, very exciting experiment. Thank you very much for that. So I'm opening the floor for questions. So let me take some from the chat. First question. How challenging is it to realize such miniature physical custom hardware component, like you mentioned, micro mirrors and controls?
Okay, so that's a rather challenging question to answer because it very much depends on the application. So there's really a parallel development between atomic physics, laser physics, and then these additional hardware components that we need. So these digital micromirror devices, they are around already for a while, and this is quite standard to integrate. Now, if you think about, for instance, this local control with this additional tweezer beams that we want in order to simulate more complex model Hamiltonians or actually do quantum computation experiment, it becomes quite challenging for hardware development as well. Just imagine you have about 2,000 atoms and you locally want to control each individual atoms with such a beam. This means that each individual beam needs to be controllable in terms of frequency, intensity, and timing. And maybe you even want to dynamically move it around. So this means you basically need 2,000 optical channels that you can send or project into your atomic plane in order to talk to them. And yeah, this also becomes actually computationally complex because you need to compute waveforms, etc. You need a lot of memory to play the waveform. So all of this actually gets also from an engineering point of view more and more challenging. And there are collaborations also with companies, and there's really this parallel development, which is now also pushed by the quantum computing community.
Great, and worth to mention that those 2,000 beams, all of them need to be very fine-tuned and very stable and very well isolated, etc., etc. So, and
diffraction limited. So actually also from an optical design perspective, that's very challenging because we have this high NA objective, and each one of them needs to be diffraction limited to a small spot of only a few hundred nanometers. And having that over a large field of view is, of course, also very challenging.
Yeah, wonderful, wonderful. Thank you very much. Another question: what's your software arsenal to keep track of all your equipment, test and measure its components?
Sorry, can you repeat?
So the question was, what's your software arsenal to keep track of all your equipment, test and measure each component? So I think this may also be a little bit challenging to answer.
Yes, because it has many different parts. So we have a control software, which actually is written in Python in order to send the commands to the different devices. So we have a central computer that keeps track of the real time. And then we have the second big part, which logs all the data. So we have a lot of monitoring equipment for intensities, frequencies. We have a lot of frequency logs that need to be tracked. And then they are collected and stored in log files, which we can then actually display with a Grafana software to even check remotely from home if the lasers are still locked or if the intensities still reach the values that we need. So there's of course all this software behind which allows us to make sure that the experiments are run in a controlled way.
Great, thanks. Another question. So it's actually a question that I wanted to ask too. So you have shown in your talks talk that you are using the Hubbard model on a square lattice. So the question is it possible to do triangular or even Kagome lattice with the anti-fragmentary Hubbard model to study fluorescence? So you may know that Kagome lattice is now becoming more and more famous. and more used for, especially for exploration of topological order of matter.
Yes. So all of this is possible and has been demonstrated. So there are hexagonal lattices, triangular, Kagome, LEAP, all sorts of lattices, the quasicrystals that I mentioned. So anything really that can be engineered by interfering laser beams. So you just have to find the clever configuration. And there's a second type of platform that I didn't really talk about, which is this Rydberg atom array platform. So the idea is that you don't have tunneling between neighboring sites, but there are interactions induced by excitation to Rydberg levels. And here the atoms are trapped really in individual tightly focused laser beams. And those can be arranged in arbitrary configurations. So you can place them even in aperiodic structures if you want.
And that was exactly the topic of talk by Igor earlier on the previous session. So yeah, I wanted to ask you the question just for our audience too. Can you please highlight the difference between the two approaches? So the Rydberg optically trapped atoms and the approach that you are taking here, both on the methodological aspects, but also on the outcomes.
Yes, sure. So let me maybe just briefly jump to, sorry, did I stop? No. Do you still see it? Yeah.
Yeah, still seeing your screen.
Let me just briefly jump to the other slide in order to explain that maybe a little bit better. So this overview slide. So in this case, you have a periodic potential where the distance between neighboring sites is very small. So it's on the order of lambda, like half a micrometer, such that you can actually have coherent tunneling between neighboring sites. So the atoms really move in space, and the basic interaction is then given by them sitting on the same site and moving around. This gives you the Hubbard model. And you cannot generate any arbitrary configuration, but like Kagome, LEAP, yes, all that works. But anything that you can generate on these small length scales. Now, the other approach where you have the Rydberg atom arrays, the length scales are much larger. So typically you have an array of tightly focused laser beams where the distance between them is on the order of a few micrometer. So I also have a picture of that. So this is an example from our Ytterbium lab, for instance. Again, these blue dots are individual atoms, but the distance is 5 micrometer. So there's no tunneling whatsoever. You have to do something else in order to engineer interactions. And this is done via Rydberg excitations. And these allow you to study spin models. So the atoms do not move around, but you play really with the occupations in the Rydberg levels. And those, because you have this array, which is shown here in terms of AUDs, but you can also generate them with SLMs. Here, the location is essentially free to choose depending on where you send the trap. So these are the two different types of experiments. One where you have coherent tunneling and Hubbard type models. And here you have spin models that you implement. And the length scales are very different. So the distances between neighboring sites are very different.
Awesome, thank you very much, Monika. So I will pick up a very last question. So who would be the best contact person to discuss open PhD position?
Me.
Great. Very straightforward, very efficient answer. So